Now we're really going to get into the C programming language. We're going to start talking about controlling the flow of your program. All that we have seen so far in Hello World was just one line. There wasn't any place to go. There wasn't anything else to do. Just the one line that formatted, printf, Hello World. Well, now we're going to get into real serious programs. We're going to create bunches of statements. We've called them expressions so far, but when you stick a semicolon on the end of it, it becomes a C programming statement. And we're going to look at blocks. Blocks are bunches of statements together, and I'll show you how we block those together. We use braces around them, and we'll talk about braces and blocks of statements and how they occur and how you control them. We'll look at an if-else. If this is true, do this, else do something else. And we will look at else-if, which can be combined with the if-else to form a bunch of decisions together. The switch is a larger construction which lets you switch on let's say a character that somebody typed in. And if they put in an A, go do this, a B, go do that, a C, so on. We'll look at switch. We'll look at a while loop, which does something while a condition is true. A for loop is kind of like a counter. You start here and you go to there and you increment by so many for a number of turns to the loop. A do while is an upside down loop. We call it an exit controlled loop. And you do something while something else is true. And that forces us through the loop at least one time. We'll look deeply into do whiles. There are a couple of statements that can be used inside all of those others, and that's break and continue inside those other loops. And then finally, we'll wrap up with the goto and the labels and how to use goto and labels in controlling the flow of processing of the computer as it runs through your program. So hang on, and here we go. Now we're going to talk about statements and blocks, or blocks of statements. An expression, what we've seen so far, like A equals B plus C, with a semicolon on the end becomes a statement. So we've talked about how to make expressions, all the precedence of operators, things like that. Now we're going to turn expressions into statements of work. Those statements of work are then grouped together into a compound statement or a block of code. The blocks of code then can be managed. How do you get into a block of code? How do you get out of a block of code? How many times do you perform a particular block of code in a loop? Those compound statements or blocks are noted by braces. And you can see braces right there. We have an open and a closed brace. They're not squiggly brackets. They're not weird parentheses or anything like that. I've heard them called all kinds of stuff. They are called braces. And braces group our statements into compound statements or blocks. We've already seen braces. You remember when you created main and then you had open close parentheses, different little animal, and then you had an open brace. Well, that surrounded all the statements, in our case just one, of that printf of hello world. The braces surround all the statements of the function definition. And we'll see that braces surround multiple statements in loop constructions too, when we start creating loops, which is just very shortly here. Now here's our little main program again, and it is, or contains, I should say, a block of statements. And there's the open brace. Notice there's no semicolon or anything here though. And there's the closed brace. Again, there's not a semicolon when you use a construct like this, when you have the open brace and the closed brace, because it's not doing any work. It's defining the statements that will make up the work. Now the work statement, something that does something, that needs a semicolon. That needs an end of line character. And that's what the semicolon does for us. It tells C, we're done with this statement. Go down to the next line and start reading again and figure out what goes on down there. And then it'll see this closed brace and go, okay, I need to match that with the brace I found up here, and it will match them up and know that that's the end of a block. Since we had open and close parentheses up here without a semicolon, it understands that it just defined a function. This is the stuff that makes up main inside the statements and blocks. When we're doing a loop, there is a while loop. Look at that, it doesn't have any braces. Well, that's because it's only controlling one statement. It has this semicolon out here. So that tells us that a number of statements inside braces, like this, are a block of code, or a statement block, a compound statement, which is the same as this one little simple statement right here with the semicolon. So that means that this while could control a bunch of things if there were only a brace between the while and the printf and then after it to close this up. So let's take a look at that. There we go. There's an open brace. And now we can put a whole bunch of statements in here, hundreds and hundreds of them. And you shouldn't do that. You shouldn't have a while that's that big. But you could put a whole bunch of statements in here, and then there's our close brace. C will keep it all straight because it remembers how many braces it has seen, that it has opened, and another open, and then a close, and then another close. So the compiler will keep track of all that. So that's a statement block for a loop. Now some people like to program this way. They put this brace out here at the end, and then they tag the closing brace underneath at the same tab stop, underneath the opening statement or opening reserved word of the loop. That's not the way I was trained, though that's the way you'll see a lot of C programming done. I tend to lose this brace if I put it out there on the end. You'll see this a lot in magazines if you see listings, because remember, magazines sell by the inch, so they don't need one more blank line taking up space, so they'll put their open brace up here after the parenthesis, just so you know what's going on. This is the way I was trained to do open and close braces. I put them underneath the W of the reserved word of the statement of the loop. So here's the while loop, and here's the test, and we'll see that when we talk about these kinds of loops. But there's our test, and this is the work that's being done for the while. So I have an open brace there and a closed brace there, and it's real easy for me to scan down the page and find these braces, and then fit in whatever lines and function calls and things like that that I need in here. So that is statements and blocks with loops, and we've looked at braces and how braces control a number of statements to make up a compound statement. Well, now let's take a look at the if-else construct. Now, mostly you'll just see this as an if statement, but the else is part of it. It's optional, though, so you certainly don't have to have an else. Many times you won't have an else. It'll just be the if. What we do is we say if this test expression resolves as true. Now, to remind you, what is true? True is non-zero. So if the result of this test expression is non-zero, it will be true, and this statement will be performed. What else could be in here besides a statement? A statement block. You could have an open brace here or here. Remember, C doesn't really care about white space. And then a number of statements inside the statement block, which get executed if this is true. If this is not true, and what is that? That is zero. That is a zero result. If the result of the test expression is zero, we come down here and we perform the else false statement block. So if this is true, do this, else do that. It's very simple to read it through. Here it is with a statement block and a single else false statement. If this is true, do everything inside the braces, whatever these statements are, and that all equates to be one statement block. Else, do this statement. And then, of course, here's the whole thing. If this is true, do this block, else do that block. And we'll have a chance at the end of this section for you to write some code using if-else. So if-else is pretty easy. If the expression is true, do the first group, else do the second group. Now we need to take a look at the else-if construct. We already looked at the if using an else afterwards, but there's a new construction here called else-if. Take a look at this. If the test expression is true or non-zero, then we run this true statement. We've seen that. And then we come to the else. Well, now we have another if. Here's the else-if. If this test expression is true, we do this statement. Else, if this one is true, we do that statement. Else, if this one is true, we do this statement. And then if none of these test expressions up through here are true, we'll wind up doing this none of the above here at the bottom. There's no practical limit to the number of items you can have in here that you can stack up in the else if. We have a better way to do this that you're going to see in a few minutes in the switch statement. But for just a few options, like testing options on a command line, the else if works just fine. Let's go take a look at a program using the else if, and I'll show you how it works, and we'll talk about that program. Here's my Visual Studio prompt, and I have a notepad open here with the program in it that I want to show you. Just a little something I whipped up for just us. Here I pick up standard I/O, pretty normal. Here we have our main, and notice we're starting to add a few items here in our main declaration. Here we're saying that main will be able to return an integer back to the operating system, which is how it tells the OS whether it ran okay or not, how things went during the function, during the work of main. Here we have the first parameter to main is always an argument count, and traditionally it is set up as an integer, and it's called argc. Obviously, this is just a variable name, and you can call it whatever you want to call it. Just know that the first thing that is passed into main will be a count of how many arguments come from the command line. The name of the program that you run, and this one's going to be called else if, is always the first parameter. Argc will always be at least 1 to show that there was one argument, the name of the program itself. Here is a character pointer array. Don't worry about that too much right now. I promise we'll talk about the details of character pointers and how they work. But what this is a list. It's an array. So it's more than one thing. It can be a number, and it will be however many argc is. If there's 1, 2, 3, whatever is in this. It is a list of pointers to the words coming from the command line. The first word will be the name of the program. The next word will be whatever is between a couple of spaces on the command line, and the next word, and so on, as we do our command line. And you'll see how this works here in just a minute. Here's a little quickie automatic character buffer. We named it buffer. We call it whatever we want to. It is 10 characters long, so it's kind of short, but it's good enough for us. And it is made up of individual characters. It is also an array, because there are little square brackets there. So we've asked the compiler to set aside 10 characters in memory for us. Now we're going to do a test here, because if we don't do this test and we try to do some things with the arguments down here, if they don't exist, we'll blow up the program. And we get that little send error report to Microsoft, or don't send, or so on, if we touch things in memory that we really shouldn't be touching. So if the argument count is less than 2, that's a problem, because we want the argument count to be at least 2, which is the name of the program, and then one option coming in, 1/? Or something like that. So if it's less than that, the person hasn't used the program right, so let's get out of here. We'll printf usage, we need an option, a new line, and then we'll leave with a bad exit code with an exit 1. And exit 0 is a good, clean exit. Exit 1 says, oops, we had a problem. And then we're done. We're out of the the program at that point if the argument count is less than 2. Let's say that our argument count is greater than 2, which is what we need. We'll continue past our if on down to here. This is a function that we haven't talked about yet. It's one of the standard string handling functions, and it's pretty easy to use, as you can see, and it's called string n copy. And string n copy will take a number of characters from the second item and put it into the first. So here's buffer is our destination. Here's the source, which is the first argument, past the name. If we put a 0 in here, that would be the name of the program itself. argv sub 1, though, is our first parameter, and we're going to take a maximum of 9 characters. Remember that C strings always have a 0 on the end of them. They always have a null byte. So this is 10 characters long, so we don't want to use them all up. We need to have that last one as a 0. So we'll only copy 9, a maximum of 9 across. That's a way of keeping somebody from overrunning our command line and messing things up. We'll see more of that later when we talk about web programming too, because that's a common way to have a web person mess with us. So here we say, if not string compare buffer / question mark, printf, they want help. Now string compare, what it's going to do is do exactly that, compare the characters in the string that's inside buffer, and we know that that's our first command line argument, with this slash and the question mark. If they are exactly the same, string comp is comparing buffer and / question mark. If they are exactly the same, there is no difference between them. If there is no difference between them, that's 0, and string compare will return a 0. Well, what's a 0 inside an if? It's false. Well, we want to arrange our logic so that if this does compare properly and is true, then we'll print out they want help. That's where we use the not, the exclamation mark, or some people call it the bang. If we do not string compare, if these two are equal, string compare returns 0, the not turns it to non-zero or 1. The if works, and we print out they want help. Else if, which is why we're here, else if not string compare buffer / a, then they ask for option A. Else if not string compare buffer B, they asked for option B. Else we don't know what they asked for. They put something in the argument that didn't work, and that's the unknown option. What we'll do is save this so we know we're working with the right code, and we will come back here to our command line, and we will do our cl elsif.c, and there we compile it, and we get our program, elsif.exe. Now I'll run it. Now I notice here, I ran it without any options. So our argument count was equal to 1, and that's not enough. Our argument count needs to be greater than 2. So we wind up here. Usage, we need an option. Right there. So our argument count was wrong. Let's say that we run it though, else if, and we ask for help, / question mark. They want help. Now we're in this part. If the string compare / question mark, printf they want help. None of the other ifs or else ifs would match, so we wind up jumping out of the program here at the end. And of course we can look for A. There's option A. We can look for B, option B. And if we put something else in there, like a C, we didn't program or didn't handle an option C, that's an unknown option. So all of our test scenarios work. We tested without any option. We tested with our known good factors, and we tested with an unknown. So that's our full test suite for this particular program. And everything worked just as we thought it would. Now we will have an exercise for you later to use else if. So take a look at this program, and we'll make it available to you here for a little bit so that you can see the thing, and you will be able to use the if else and else if also in your own code. So now we've seen the else if statement. if this is true, do this. Else if this is true, do that, that. Else if none of these match, do the final default statement. This is optional, of course. You don't have to have that there, but it is nice to have this else to kind of clean up and make sure that if you don't get one of your items, that you handle that properly and don't fall off the end of the world. Well, now we're going to talk about easily one of the most powerful expressions, control structures, however we want to put it, in the C programming language. And that's called the switch or switch case. Because switch and case, and also default, are keywords in this item, but mostly it's called the switch case. And what happens is that we switch on an expression. Now this expression has to have an integer result. You can't switch on a string, you can't switch on a float, anything like that. This has to be an integer value in switch expression. Down here we will have the word case, that's a reserved word, another constant expression, because this is not being evaluated, this is actually being compared inside the assembly language that will be produced. So we have a constant expression, and then a colon, and then a statement or statement block, surrounded by braces, as we know, to be executed if this constant expression matches the original integer expression up there. We are actually comparing these two. Now the neat thing in a switch is that we can have a whole list of these, whole list of cases, and we will actually create the same kind of form that we had with the else if that we just took a look at, but this is a much cleaner way to do it, and it's much easier to maintain. And then there is a default colon statement at the end, which is optional. You don't have to have a default. If you don't, execution will run through these case constants and then fall out the end. But if you want to do something at the end, like our else we had before, then you need a default statement. Let's take a look at the two side by side, switch and else if. Here's our else if that we just took a look at in the last video. Remember, if not string compare buffer and the slash question mark that we used, if that was true, this comparison, we would print they want help. Else if, and so on, slash A and slash B, and then here's our default of none of the above, we would print an unknown option. Well, here's how we do it in a switch. We switch on buffer sub 1. Remember, buffer sub 0 has this slash in it, and buffer sub 1, the next character over, has this question mark or an A or a B or something we don't know. So we are going to switch on just the one character and skip over the slash. If, that's how you read this, if this, in case, this buffer 1 is a question mark, in case buffer 1 is a question mark, printf, they want help, just like we did here. And then we break. We have to have this break statement in here because these cases will fall through if we don't. If we don't do that break, this would occur. We'd skip right over these two values because they're just labels. Notice the colon, that signifies a label. They're just labels of the switch. And it would fall in and it would print option A, and then it would fall in and it would print option B. So we need to have that break word in there. If this question mark does not match our expression, notice that's a literal, single quotes around it. If this literal constant value right here does not match that, we'll go to the next one. And we'll look here, in case this buffer 1 is a capital A, or in case buffer 1 is a lowercase a, do this, print option A. Now we didn't have that functionality only over here. We only could look at uppercase A and B because we didn't do any conversions or anything, any lower string work or anything like that to convert these. So switch gives us a little more functionality in just one more little line of code that doesn't really produce much of anything in the compiler other than an extra comparison. So here we have a case uppercase A or case lowercase a. If that one hits, it'll fall through that one, And if that one doesn't hit, it'll catch this one, and we'll print option A. And then we break. Same thing down here, uppercase B or lower B, we'll print option B, and then we'll break. Remember, you got to have the break so that you can get out of here and not fall through. If we don't hit A or B, we'll hit the default label down here, which says unknown option, just the way we had our default else, none of the above over here. All right, so that's what this structure looks like. Let's go take a look at it in code, and I have it over here in switch.c, and you can check out the DVD or the online, and this code and the other code that we've looked at will be available to you in case you don't want to type it in. I recommend you type it in, but in case you don't really want to, you can pick it up from here. And these are such valuable programs. I don't know that you're going to gain all that much, but you should really type them in and suffer through it yourself. So here we have our standard IO include. Here's our good old main. You're going to return an int. It's going to take an argument count and our argument vector, which we remember is an array of pointers to the argument strings that come in from the command line. Little automatic character buffer, 10 bytes long. If the argument count is less than 2, they didn't put anything on the command line, and we tell them we need an option so we don't blow up, and we leave with a bad exit code, exit 1. If they did everything the way they were supposed to as a good user, we come down here to string end copy, and we copy up to 9 characters from the argument v, from the first argument v. Remember, argv sub 0 will be the name of the program itself, but we will copy this from our option that they give us into the buffer. And now that we have that, we will switch, just the way we looked at our code. Let me move it up for you here. We will switch on number 1 character. The first character is in element 0, buffer sub 0. And I know we haven't talked about arrays yet, but if you're somewhat of a programmer, you already understand zero-based indexing. So we have buffer sub 0 and buffer sub 1. The 0 is going to be the slash. We're going to skip over that. And here's our case that we just looked at. Case question mark, break, A's, break, B's, break, default. End of the switch. We have braces here to enclose all the code of the switch. And this is the end of main. This is our brace down here that matches up with the end of main. Everything makes sense? Remember that you could have braces in here and encapsulate a number of statements. It could be controlled by this particular case label. All right, so let's go take a look at it run. We'll go to our command prompt and we'll compile it. I called it switch.c. There's our compiler, and it created our object code, linked it together, and we have switch.exe, which will run with no parameters. Usage, we need an option. So that hit argc less than 2. Usage, we need an option. We're not at that test phase yet. So now we need to switch on our first possibility, which is lower A. That's option A. Switch on our next in the test suite. Option A also functions. B, yep. B, yep. What happens if we do C? Oh, unknown option, exactly the way it should be. And any other characters in there, we don't care. We see them as an unknown option. And notice a little bit of a side effect here. If we start our gibberish with a good character, that /B. Remember, we're only looking at the valid first character there after the slash. So this will match as option B, even though there's a bunch of junk there that we never look at and don't care about. So we have to decide and talk to the program managers, is that acceptable for them to put that garbage out there, or should we tell them, no, you can't do this? And then that adds more code, and that's how we make a living. So that's the switch statement as compared to the else if that we looked at in the previous video. And now you know how to make a switch. and I'm going to have you cut your own switch here pretty quickly as we give you some programming assignments and some homework to do. Let's take a little while to talk about while. The while loop, or another control statement that we've been looking at in the last few videos. While is pretty simple, but like many simple things, it can be used to produce some complex results. Now here's the while statement in its basic form. We have while and an expression. If this expression evaluates to be true, non-zero, then we will come down in here and we will execute these statements. Yes, if you only had one statement to execute, you could skip the braces because the braces are just going to bind these statements together into one block of code or a compound statement. You could say while something is true, do a one-liner that ends with a semicolon. But that's not very common, so you're most likely going to see it like this with the statements, multiple statements, other tests, other things like that going on inside the while construct itself. Let's take a look at a piece of code. Here's a little program that we'll play around with. We're going to put the computer in a cranky mood, and we're going to have it say, I bet you can't type in a 7. And we're going to set up a little automatic character called I. We'll set it equal to 0 because we're good programmers and we initialize our variables. And then we're going to start a while loop, and we're going to say while I is not equal to the character 7, not just a 7, make sure you get some single quotes around there, while I is not equal to a 7, which is what we told them they couldn't type in, we will get a character from the keyboard with getChar or getChar, depending on how you like to say that. But I is equal to getChar, and we do another little getChar here because in the programming world, when we take a character from the keyboard, the person has to press carriage return because we don't want to deal with trying to unbuffer the keyboard and accept characters immediately and all that, trust me. We just want to take in a character and a carriage return. So we need to pick up the carriage return and get rid of it, and that's all this is doing. So I is equal to getChar, throw that one away, and then we'll print out, you typed something, a character. This is the first time we've used printf like this, and we have a whole video coming up on printf later on, and it'll be nice and long, and we'll talk about all these things. But here, pretty basically, we're going to print out a character form of this value, of this integer, or I'm sorry, this character that we created up here, which will have a whole number integer value. But we have taken it in from the keyboard. We will print it back out as a character rather than the numeric ASCII value that's stored in there. And if the while, see here's the bottom of the while, there's the top of the while, we take in the character, we hit this close brace, which means we go back up to the top of the while, and we say, is it what we were supposed to get? If the I is not equal to 7, this evaluates to be true, and we come back down into here and do this again, get another character, test it, yell at them again, and go on around. If we take in a character and it is a 7, they do put in a 7, we're still going to say, you typed 7, because we don't have any way out yet. So if they type in a 7, we're going to say this, so we're still going to be rude, even though they got the right value. We're going to hit this brace, we're going to come up here to this while, and it is now, this is going to be false, because I will in fact be equal to 7. This will fail, and we'll jump to the next statement, which says I'm done. And the computer goes home. So let's go take a look at that in code. There it is there in our notepad, while.c. It's all the same code, not equal to 7 and so on. And let's pop over here to our compiler. And I already have it in there. So we will compile and link it. And then we'll run it. And it says, bet you can't type in a 7. And if I say I put in an A, he says, you typed an A. If I put a 4, you typed a 4. If I put a 7, you typed 7, I'm done. And he leaves. All right, so that's exactly what we expected it to do, and surprisingly enough, the computer did what we told it to do. So that is a normal while loop, very simple. It's a while with a simple test for inequality here. This expression just has to equate to be true. Remember that. You need to have a true result in there. Now, I want to show you a little different form of while, and that's an infinite while, an infinite loop. And that's my little definition, infinite loop, C infinite loop. You see, it's supposed to be a joke. Anyway, here's our program. It hasn't changed very much, except that we're going to get a little closer to what we expect this little game to do. We're going to say while 1. 1 is non-zero, always true. This is an infinite loop. There is no way out of this loop once it starts. Well, we've got a way out. We're going to make a way out with break. We're going to break out of this loop. Control C will also work if you get a loop that runs amok on you and you forgot maybe to put the break in. You can send a Control C character in through the keyboard and stop the thing. So here we're going to say while 1, I is equal to our get character. Here's our carriage return. Soak up the carriage return, get rid of it. Now we do a little test. If I is equal to the character 7, break. Now I put braces around it, which we know from looking at the if statement is not exactly necessary, but I like to have them. And I didn't put this one down here like I normally do because I was running out of space. So it's okay. C doesn't care about the white space, the carriage returns. It's okay to put that brace up there. If I is equal to 7, get out of here. Break works on the latest loop that it's inside. Had there been another loop in here and another loop, the breaks keep track of what loop they're in. This break knows that it's inside this while. So when we hit that break statement, it knows to go to the next statement after the close of that while. So it'll jump us down to here and we print I'm done. If I is not equal to 7, now we can antagonize our viewer and say, ha, you typed in something else. That's our same line from before. And we come back around because we hit the bottom here and come through. But this time, it works a little nicer. If I is equal to 7, they type it in. We just leave. We don't bug the person anymore, even though they hit the right character. We just leave, and we say, I'm done. So let's take a look at this program. And it is in while2.c right there. It's the same code we just looked at. We have our infinite while loop. We'll pop back over to our compiler. And we'll compile and link while2.c. There we go. Now we'll run it. And it says, bet you can't type in a 7. If we put something incorrect, he yells at us, different letters. And if we do the 7, he just says, I'm done. Because before, remember, he yelled at us. If I scroll this up, you can see it here. He says, ha, you typed a 7, and I'm done. So we have different functionality, which is closer to what our original requirement was for the program, our original specification. Let's get back here. So that's an infinite while loop. That's a different way of using while by putting a hard-coded 1 in there, while 1, and just a little different way of using the while, and hopefully you understand it a little bit better. In this video, we're going to take a quick look at the for loop and how this loop construct works. It's pretty simple. Our little demonstration program is even more simple, so let's get right to it. Here's the structure of a for loop. Inside the parentheses of the for loop, the control section, we put everything that we ever need to know about this for loop. Remember in our while loops, we had to initialize things, and then we had tests within the while loop to make something happen. Then we had to adjust a counter, otherwise we had a infinite loop in our while if we did a while 1. Well, all of that is being done right up here in the top of the for loop. We initialize the environment of this loop. We then test to see if we should continue to perform the loop, and then we adjust our counters or values or perform some other piece of work here in the adjust section, and then come back and test again. If the test is still working or is still non-zero or true, then we perform the statements, do the adjust, and keep going through this. The initialize part is only done right at the beginning of the for loop. When we come into the processing, we hit the for, we do this initialization, test if our expression is true. If it is, we perform the statement, then we do the adjust, test, perform, and so on, until eventually the test fails. When the test comes out to be false or zero, then we go to the next statement after the for loop. Now this is an infinite for loop down here. I just wanted to throw this in and show you because the items between the semicolons are optional, all of them. And if you leave them all out, the test expression defaults to true. So this is the same as our while one. And this would be an infinite for loop, and that would just sit there and run. Of course, you'd probably have a break statement down here so that you could, that's a printf. That's a typo, but we're going to leave it because we're moving on to our next slide. Here's our infinite loop with the for loop, with just the two semicolons, and I got the printf right this time. That's great. So that's our infinite for loop. It does exactly the same thing that we had done before in this little program, getting a character and testing for a 7 and so on. The only word that we've changed is the for, taking the 1 out and put 2 semicolons in, and the compiler will make the same kind of construction for us. Here's a little quickie program that counts from 1 to 10 and prints out the count. Pretty simple. Sorry I don't have a great example for the for loop, but the for loop is just a nice solid construction and it does the job. And let's go take a look at that. Here's our code with our integer I set up to 0. We're going to initialize I again right here, equal to 1. We're going to make sure that I is less than or equal to 10, and we know in fact that it is at this point. And then we're going to come down here and perform whatever is in our statement block inside the semicolons. Yes, you could leave semicolons inside the braces. I hope you caught that. You could leave the braces off of here, and if you did, you'd just control the one statement as it is. We're controlling a compound statement. This is the way you'll normally see a for written. We perform our statement, perform our adjustment, which is I++, do our test. Is it still less than 10 or less than or equal to 10? Yes, it is. And we will keep running this loop out here. Let's go see it work. Compile it. We run it. There it is, 1 through 10. Aha. So that's pretty simple. And I just wanted to prove to you that it really does work. It's a good little construct, the for loop. Puts everything right at the top there for you, so it's easy for you to find and read. Be careful of the braces down here. If you forget a brace or you forget these 2 braces, the for loop will wind up just controlling the single next statement rather than the entire block. And remember, it's bad to, even if you have a single statement, it's bad to leave these braces out because somebody's going to come along and throw another statement in underneath this to be controlled by your for loop. And then they'll wonder why the code doesn't work right because the for doesn't have a statement block. It's only controlling one statement. And that's the for loop. Now we're going to take a look at the control statement called a do while. A do while is an example of an exit controlled loop. What we've looked at so far are basically entrance controlled loops, where the loop construct decides whether statement processing, the flow of processing, is allowed to get into the statements contained within the while. A do while decides, since it's an exit controlled loop, whether we are allowed to leave the statement processing, whether processing flow is allowed to leave. So here you can see we have the do, an open brace, a number of statements to be performed, a closed brace, and then the while. Here's our test expression at the end of the do while. So all of these statements are performed first, then the expression is evaluated. If this test expression returns true, as we know, non-zero, then the statements are performed again. And then the test expression is evaluated again. If it's false, we move on. If it's true, we do the loop again. Pretty simple, but necessary. Here's an example of some code. Normal headings up here, standard IO, and all the usual things we've looked at. And now we're going to do a getChar, throw away the carriage return again. We need our second getChar. And we're going to print out the ASCII, the American Standard Code for Information Interchange, value, the decimal value of this character that we brought in from the keyboard. And that's going to be I down here. So we're going to print out the decimal representation with %D, while the I is not equal to a capital Q for quit. And that's, remember, a character constant, has single quotes around it. And then notice that there's a semicolon out here at the end of the while. That's necessary in a do while. If you had a normal while, remember a few videos back we talked about while, what would happen if you had a while like this with a semicolon at the end? Well, you sit here and chase your tail, because this gets performed over and over and over again, and there's nothing in here in the statement block. No work is being performed. So this basically just sits and spins because you don't ever change I over here. Well, in this case of a do while, it's necessary to have the semicolon to tell the do while that it's done, and it knows how to get back to this open brace and start over again. So let's go take a look at it. There's the code, what we just looked at. While I is not equal to Q, we'll go over to our compiler, and we'll compile and link do while. There it's linked up. Now let's run it. I can type. And it's sitting there waiting. So in lowercase a is a 97, a capital A is a 65, and all of these other characters that we can type in there and get their values. And we do a capital Q, and we're out of the loop, just the way we said it would work. And that's a do while, exit controlled loop. Let's take a minute here and talk about break and continue. Break and continue are kind of special exceptions that can be used inside the for loop, the while loop, the do while, and the switch that we've already taken a look at. Break causes execution to exit the loop or the switch immediately. Remember in a switch we had multiple items and we had to put a break after each one so that we could get out of the switch? Well, this is the same break. We haven't seen continue yet, but what continue does is it causes the loop's execution to jump right to the test section. If it's a do while, it jumps to the bottom, to the while expression. If it's a normal while, the continue skips over all of the rest of the statements of the while that are after the continue and jumps up to the expression to see if we should leave or not. In a for loop, a continue causes execution to stop what it's doing and jump to the adjustment, the rightmost part of the for loop after the second semicolon, so that the adjustment is made, then the test is made, and we decide whether to go on into the top of the for loop again. Continue just lets you get past some kind of negative results or negative situation that you know darn well you should not run the rest of the loop. And there's no reason to continue on processing. You've hit an error, the end of a line, something like that, and you want to quit doing what you're doing, but you don't want to leave the loop yet. You want to continue processing more information. Break means you want to get out of there right now. Let's go take a look at a quick example of continue. Here's our little program from before that takes in characters and prints out the ASCII value. This is what we did with our do while statement a few minutes ago. If I, however, here in our continue, if I is equal to a capital X, we'll just continue like it never happened. And the continue will jump us over this down to our test. Our test will still not be false, It will not drop us out. I will still not be equal to Q, so we'll come back up here and we'll get another character. We'll just completely ignore the letter X if somebody types that in. Okay, so let's go over and make that happen. I called it break.c, and there it is. Let's run it. So it's sitting there waiting, and it does what it did before with different letters. But notice this time, if I put an uppercase X, it just ignores it and asks for another letter. And then eventually, an uppercase Q will stop the program, just like it's supposed to. But that shows you that the continue did its job and made us jump over the rest of this loop down here to our test. Very simple, but still powerful and very necessary to save a lot of execution time and to make your programs much more efficient and easier to read. The break is absolutely necessary in the switch, or the switch just couldn't, switch case just couldn't work without the break. So that's break and continue. I'm going to take a very short period of time here to talk about goto and labels. What I always told my students in my classes over the years is that we would discuss goto in the goto section of the class, and there is no goto section of the class. They even tell us in K&R that goto should be used very rarely, if at all. It should only be used as a last resort if you can't figure out a better way to code the thing. And I guarantee you that there is a better way to code the situation you're in without using a goto. The gotos are difficult to maintain because they cause jumps to occur right in the middle of your code. And they create what can be termed as spaghetti code, because that's what it looks like when you're trying to maintain it and you're trying to follow a thread of execution through, because all of a sudden you're down deep in a loop and you see a goto, some label, and now you have to find that label in the code. Hopefully they put it out in the first column to the left side so that you have half a chance of finding the thing. You have already seen a label in the switch statement. The cases are labels, because we said case this and that and something else. Those are labels which create a jump table inside the object code. We don't really want to get into all that here, but that's what happens, and that's how a switch case functions. Well, that's the same thing that happens when you use a label in your normal code. You wind up creating a jump point, and then the goto causes a radical jump to that other location. The compiler, when it sees this happen, has to figure out how to clean up the stack and how to take care of all the variables and other things you left lay around when you jumped out of the code. So I'm not even going to show you a piece of code using goto and labels. If you do any maintenance of C, or you just look around on the net for goto or just some poorly written C code, you'll find plenty of goto and labels out there. It'll be up to you to figure out how to maintain them. And then I think you'll agree with me that there was probably a better way. So goto and labels, don't do that.